Good afternoon, everyone. My name is Lianghong. Today I'm going to talk about a new elastic storage system called SpringFS that bridges agility and performance in elastic storage designs. This is a joint work of my collaborators from Carnegie Mellon University and Intel Labs. So, elasticity in distributed storage means that the ability to dynamically resize as workload varies. Elastic storage is more difficult than elastic computing because storage servers contain substantial states, and resizing distributed storage involves a lot of expensive data migration. The benefits of elasticity are kind of similar to those associated with elastic computing. It allows storage servers to be temporarily reused for other purposes or turned off to save machine hours, which in turn reduces the operating cost. However, nowadays, most distributed storage systems are not elastic. This is primarily because they are designed mainly for load balancing instead of elasticity. For example, the famous Google file system and Hadoop distributed file systems. In these systems, deactivating only a small number of servers may lead to a high probability of data being unavailable. So there has been some previous work on elastic storage designs. We have proposed a new design called SpringFS. Our work has two main contributions. First, it identifies and fills the gap between state-of-the-art designs. Specifically, let's take a look at two leading examples in the literature, namely Sierra and Rabbit. Sierra provides only some extent of elasticity, but can provide maximum peak write performance. Rabbit, on the other hand, provides maximum elasticity, but is unable to deliver the maximum peak write performance. As you can see, there is a considerable gap in the trade-off space between these designs. So SpringFS bridges these two separate endpoints in the trade-off space, and it can behave anywhere in between in a dynamic way. The second contribution of our work is that we propose and address the agility issue in elastic storage research. So by agility, we mean the speed of elastic resizing. Agility is important and indicates the usefulness of elasticity, as we will show in the next slide. SpringFS addresses the agility issue by minimizing data migration involved in the resizing process. As a result, it also minimizes the machine hour usage. The amount of data migrated and the number of machine hours are the two key metrics to evaluate how good an elastic storage system is. Now, let's answer the question of why agility is important. This figure shows you the resizing actions of elastic storage systems in face of a bursty workload. The workload is a randomly picked 4-hour-long Facebook HDFS trace. The x-axis is time in minutes, and y-axis is the number of active servers required by the elastic storage system to satisfy the performance requirement. The blue line here represents behavior of a very agile system that can resize in the granularity of 1 minute. In fact, the shape you see here is quite close to the shape of the actual load. So previous elastic storage systems usually rely on very infrequent changes. The red line here shows the resizing action of a less agile system that can only resize hourly. For each period, the number of active servers corresponds to the peak throughput in that period, as is done in Sierra as to avoid significant latency increase. The gap between these two lines, as indicated by the shaded region, shows that over half of potential savings is lost with such infrequent resizing approach. The key takeaway in this slide is that better agility allows elastic storage systems to more closely track workload variation so as to achieve lower machine hour usage. Next, I'm going to talk about some notable previous work in elastic storage, describe their limitations, and highlight the need for new design. Let's first take a look at a non-elastic example, the HDFS. In this figure, I'll focus on the HDFS data layout and explain why it makes the system non-elastic. Assuming we have a total of n servers in the cluster, the x-axis is the server number ranging from 1 to n. The y-axis means the amount of data stored on server X for each point on the x-axis, from 0 to 100% capacity. For clarity, the dashed vertical lines here represent the boundaries between servers. HDFS uses a pseudo-random data placement policy, which leads to an even data layout. Assuming the default three-way replication is used, the first replica of all data are distributed across all servers. So do the secondary and tertiary replicas. Such an even data layout is good for load balancing and performance. However, deactivating only a small number of servers may lead to a high probability of data unavailability. In other words, the key takeaway is that in HDFS and systems using a similar data layout, almost all servers must be on to ensure 100% data availability at all times, indicating little potential for elastic resizing. Recent research in elastic storage has provided different mechanisms for data placement, but the general rule of all these designs is more or less the same. Essentially, they take advantage of replication, originally for fault tolerance. The key idea is to keep all primary replicas on a subset of the cluster called primary servers. As long as these servers are active, data availability is always ensured. The other backup replicas can be activated on demand. Note that the consistency model is not broken here because we're still maintaining 3 replicas for all data. It's just some of them are temporarily deactivated when performance requirement drops. I'll talk in more detail about 2 notable elastic storage examples, namely Sierra and Rabbit. I mentioned them before, but let's now take a closer look at how they provide elasticity using different data layouts, mechanisms, and why we need a new design. This figure shows the data layout of Sierra. The meaning of axes are the same before. Instead of distributing all replicas randomly across all servers, Sierra explicitly placed the primary replicas on the first 1/3 of the servers. It places the secondary replicas on the second third of the servers. It places the third replica on the rest servers. The benefit of this data layout is that Sierra can deactivate up to 2/3 of the servers without any cleanup work, essentially that's the secondary and tertiary servers. We are particularly interested in 2 properties in elastic storage data layout. The first property is the peak write performance that the system can provide. We don't mention read performance because all the systems we are comparing here provide the same read performance given the same number of active servers. So for Sierra, the peak write performance it can provide is as good as HDFS, which is aggregate write throughput of n divided by 3 servers, because each data block is written 3 times. And we are happy about that. The other property we are particularly interested in is the number of servers containing primary replicas. This property is important because servers with no primary replicas can be deactivated immediately without any cleanup work. For Sierra, this number is n divided by 3. However, only being able to shrink to 1/3 of the cluster size is not quite satisfying, especially when workload is low. Rabbit, on the other hand, organizes its replicas according to a so-called equal work data layout. It uses a very small number of servers to store the primary replicas, shown as a P in the figure. Such a small number of primary servers allows Rabbit to shrink to about 13% of the total cluster size without any cleanup work. In fact, theoretically, Rabbit provides best elasticity in elastic storage designs, and we are very happy about that fact. However, the primary servers may become performance bottleneck during writes, and the peak write performance the system is able to deliver is limited by the P primary servers, because every write has to go to those primary servers. Rabbit does provide a way to solve the write performance degradation problem I just mentioned before. When write performance becomes a bottleneck, Rabbit temporarily offloads write requests from heavy loaded primary servers to all active servers. Now, the peak write performance is as good as HDFS. However, due to write offloading, primary replicas are spread across all servers. As a consequence, whenever Rabbit needs to decrease its size, it has to migrate some amount of primary replicas to the remaining active servers to ensure data availability. In this case, when Rabbit uses offloading, it behaves similar to HDFS, but will restore the equal work data layout afterwards. The enforced data migration largely impairs the system agility. We have described the data layout designs of several elastic storage systems. Now let's summarize them in this trade-off space. The x-axis is the peak write performance that the system can provide, normalized to the throughput of a single server. Higher is better. The y-axis is the number of servers with primary replicas. Lower is better because the other servers with no primary replicas can be deactivated immediately without any data migration. This figure shows you the very different design points represented by Sierra under all cases, Rabbit without offloading, and Rabbit when it uses offloading. Note that due to the rigid data layout used in Sierra and Rabbit, they have to make somehow painful trade-off among performance, elasticity, and agility. SpringFS provides a more flexible design that provides the best case elasticity of Rabbit, the best case write performance of Sierra, and much better agility than either. SpringFS achieves the range of options in between using a new technique called bounded write offloading, which I will describe next. The SpringFS design mainly consists of three techniques. With bounded write offloading during writes, SpringFS will constrain the distribution of primary replicas in a dynamic way as workload varies. With read offloading, the system preferentially offloads read from write-heavy servers so that the need for write offloading is reduced. With passive migration, SpringFS delays part of the migration work when servers are reintegrated, in the hope that the delayed work can be replaced by future writes. Due to the limitation of time, I will only focus on one of the techniques, which is bounded write offloading. I encourage you to read our paper if you want to know more about the two other techniques. To retain the great elasticity of Rabbit that is theoretically the best, SpringFS uses a variant of the equal work data layout, as shown in the dashed lines. The idea of bounded write offloading is actually simple. When write performance requirement increases and offloading is needed, instead of distributing primary replicas across all active servers, these primary replicas are constrained only in the first M servers. So this number of servers are the smallest possible number of servers, just enough to satisfy the performance requirement. And this set of servers receive only one complete copy of primary replicas so that they can focusing on addressing write requests. Because servers in the offload set are dedicated to primary replicas, writes that would have gone to servers between P and M, which are normally the secondary replicas according to the original layout, are then load balanced across all active servers, which end up going to the higher number servers. The important takeaway is that the size of the offload set is not a rigid setting, but can automatically adapt to workload changes. It not only determines the peak write performance of the system, but also determines how many servers can be deactivated without any cleanup work. The calculation of this p-value is pretty straightforward. Essentially, it is decided by the aggregate write performance at that point of time divided by the throughput a single server can deliver. When write performance requirement drops, SpringFS can reduce the offload set down to P, in which case it behaves like Rabbit. When write performance requirement goes up, SpringFS can increase the offload set to up to n divided by 3, in which case it behaves like Sierra. In addition, SpringFS provides ranges of options anywhere in between Rabbit and Sierra. So our system is implemented as a modified instance of HDFS, mostly written in Java and Python. We built and used a scriptal HDFS interface that allows quick prototyping of new policies for data placement, load balancing, and data migration. As a result, we can implement SpringFS and Rabbit in the same system. We have also implemented a resizing agent that is able to activate and deactivate storage servers according to workload changes. We evaluate SpringFS with a prototype as well as real-world traces coming from various Hadoop deployments at Facebook and Cloudera customers. We find that SpringFS improves over state-of-the-art designs in that it significantly reduces data migration involved in elastic resizing, that it reduces machine hour usage, often close to the ideal case, and that it provides ranges of options between the previous designs. In this slide, I will show you the amount of data migrated in SpringFS with varied offload set as compared to Rabbit with and without offloading. The experimental setup is as follows. You can show that on the upper right corner. We use 30 data nodes. 4 of them serve as primary servers. We write 2 GB of file on each server with a 128 megabytes block size with 3-way replication for all data blocks. The x-axis means the target number of active servers ranging from the total cluster size to the number of primary servers. The y-axis means the number of blocks to migrate if the system decreases its size to x servers for each point on the x-axis. Now, as you can see, which is shown by the pink line, when no offloading is used, Rabbit can shrink its size to the number of primary servers without any data migration. When offloading is used, as shown by the green line, decreasing any number of servers in Rabbit would incur some amount of data migration. This is because primary replicas are distributed across all active servers due to offloading. The red, blue, and yellow lines in between represents the cleanup work by SpringFS, with offload set equal to 6, 8, and 10 respectively. As offload set increases, the distribution of primary replicas expands, and the amount of data migration increase accordingly. Perhaps the most interesting observation lies in the difference between the Rabbit with offloading and SpringFS with offload set equal to 10, which corresponds to the green line and the yellow line. Although they provide the same performance, there is a considerable difference in the amount of data that they need to migrate when decreasing cluster size. This shows the effectiveness of the boundary right offloading technique. In addition to the experiments with SpringFS prototype, we also analyzed the behavior of SpringFS on the real-world workload. We have a total of 6 real-world traces, and the paper provides results for all of them, but I will show you the result from part of the Facebook trace as an example. In fact, we have observed similar trends across all traces. You might recall that this figure appeared before when I explained the importance of agility. The meaning of axis and the 4-hour-long trace here are exactly the same as before. The blue solid line here represents the number of active servers required to satisfy the performance requirement by an imaginary ideal system for which no data migration is required at all for resizing, and it overlaps perfectly with the actual load. The resizing interval is 1 minute. The area under the curve indicates the aggregate machine hours used by the system in the 4-hour period. So the less, the better. This figure shows how SpringFS behaves as compared to the ideal system under the Facebook workload, where SpringFS corresponds to the red line. I want to let you know that we started trace replaying more than 3 days before this 4-hour period. So what you can see now represents the system behavior when the system is operating in the stable state. As we can see, in various points of time, when SpringFS decreases its sizes, There's almost no cleanup work involved at all, thanks to its agility-aware offloading policies. However, SpringFS cannot shrink its size below the number of primary servers, as indicated by the dashed gray line. This explains the visible gaps between SpringFS and the ideal system near the bottom of the graph. You might not be able to notice it, but there is indeed some difference between SpringFS and the ideal system when increasing the system size. This is because some extra number of servers need to be temporarily activated due to passive migration. We have also repeated our analysis for Rabbit and Sierra across all traces. Here we show you the summarized results. The x-axis are the 6 traces we used for analysis. CC stands for Cloudera customers, and FB stands for the Facebook trace. The y-axis represents the aggregate number of machine hours used by SpringFS, Sierra, and Rabbit, normalized to the ideal system, which corresponds to 1 on the y-axis. SpringFS improves over state-of-the-art designs by 6 to 120% in terms of machine hour usage. For some traces, for example, CC-D, CC-E, and the Facebook trace, SpringFS actually falls within 5% of the ideal machine hour usage. So in addition to machine hour usage, we also analyzed data migration by these elastic storage systems under the same 6 traces. Again, the x-axis represents the 6 different traces. The y-axis here represents the amount of data migrated during elastic resizing by SpringFS, Sierra, and Rabbit, normalized to the results of Rabbit, which is 1 on the y-axis. It turns out that SpringFS reduces data migration by up to 2 orders of magnitude as compared to the state-of-the-art designs. To conclude, we have designed and implemented a new elastic distributed storage system called SpringFS that fills the gap between state-of-the-art designs in the trade-off space among performance, elasticity, and agility. Agility is important, and we show that good agility enables elastic storage to closely check bursty workload, which is common nowadays. SpringFS explicitly addresses the agility issue by minimizing the amount of data that is needed during elastic resizing. Some of the key techniques include bounded write offloading, read offloading, and passive migration. In the last, using experiments with SpringFS prototype and some real-world traces, we show that SpringFS significantly reduces data migration and achieves much lower machine hour usage than state-of-the-art designs. Thank you for listening to my talk, and now I'm ready for your questions.
Mohammed Khatib, HGST. Can you shed some light about the control loop that you use to pursue the workload change?
Can you say it again?
I'm interested in getting some information about the hysteresis of the control loop you use in SpringFS to pursue the changes in the workload so you adapt the number of active nodes.
Okay, so you mean what is the tool we use to predict the performance ahead of time so that we can adjust this offload set value, right?
Indeed, yeah.
So in this paper, we actually, we didn't design this part of workload prediction. So for the analysis, we just assuming we have a perfect predictor. But there has been several previous work on workload prediction that I think can be well integrated into our work.
Right, so the graph that you showed where the red curve intersects completely with the blue curve will be delayed by some time.
Yeah, it will be delayed by some time, but so because we were assuming a perfect workload predictor, but we think the relative benefits of using a more agile policy will still hold.
But wouldn't then Rabbit work as good as SpringFS in that regards if you have an Oracle in your system?
Sorry, what?
Wouldn't Rabbit be as competitive as SpringFS in exactly matching the number of nodes?
No, because what Rabbit does is when the performance requirement is not met, it will spread all the primary servers across all active servers, right? And even if you have some delay in terms of workload prediction, that property is still maintained in Rabbit. And the relative benefits of SpringFS, which is constraining the distribution of primary replicas, still holds, even if there's some delay.
Good, thank you.
Thanks.
Two quick questions. First of all, it's a bit an exaggeration to say that HDFS placement policy is random. It's a bit more complex, and the sense of it is that it tolerates failure of a whole rack. So with your policy, does it tolerate rack failures?
Yeah, so I think what you're asking is about how we deal with fault tolerance, right? How we deal with failures, right?
No, the rack is a set of computers, right?
Yeah.
With a common switch. So if the switch fails, that means that the whole rack fails. And HDFS tolerates that.
Yeah.
With your policy, does it?
Yeah. So HDFS has a pseudo-random placement by that. So it places the first replica
that's
locally.
what I'm saying. It's not pseudo-random.
Yeah. So it places its first replica locally, right? And it places the second replica on the same on another machine on the same rack, right? It places the third replica on another machine on a different rack, right? And that's what you are talking about by saying that HDFS is able to tolerate such rack failure, right? So we are not. So our system is a modified instance of HDFS. So we are still maintaining 3 replicas, and these 3 replicas can still respect that the notion of racks or different racks at the same rack, something like that. We are preserving that property. It's just that we can temporarily deactivate some of the backup replicas, but the consistent model is still maintained.
Okay, very good. And the second thing is, what do you exactly mean by offloading nodes? And how do you do that on a per minute ratio? Because reloading a data node can take tens of minutes.
Are you talking about the offloading we use in SpringFS or the
SpringFS? What offloading means?
Offloading essentially means the writes that would have gone to. So if you use the Rabbit data layout, right? There are a small number of primary servers, and they will become the performance bottlenecks because every write will go there, right? Offloading means offloading actually means redirect requests that would have gone to these heavily loaded servers to a relatively lightly loaded servers.
Okay.
Yeah, thanks.
Hi, really fun paper. I'm Keith Smith from NetApp. Some people have looked at HDFS and sort of the triple replica thing and said, gosh, that really wastes a lot of space. Why not do RAID or some form of erasure coding? So sort of, how does that look from your perspective? Would you argue I'm better off with replicas because I can do the dynamic thing then?
So we haven't talked about erasure coding in this paper, but I think that in order to make storage systems using erasure coding, Elastic needs some different designs from what we are using here. Because all this approach we are assuming is using replication. But I think that's still a reasonable assumption. Thanks.